So hard. It's so hard.
Can you, on both computers, next time? All right, you're good to go.
So thank you everyone for coming. We are here to present our final design review. Our team name is Servers Down and our project name is All Weather Lane Departure Warnings.
I'm Rifki. I'm one of the programmers on the team.
I'm Akilish, and I'm also one of the programmers of the team.
I'm Dev Patel. I'm also one of the circuit designers on the team.
And I'm John, I'm also one of the circuit designers.
So as most modern cars have this useful feature called lane departure warning system that basically assists you for any unintentional deviation. It alerts the drivers. One of the major drawbacks of this system is it does not work during harsh weather conditions because of the low visibility of the lane markers. So to address this problem, our team decided to have a proof of concept, and that basically defines the project statement of our project, which is lane departure warnings does not work when there's debris such as leaves, snow, and it's covering the lane markers as you can see here. This causes difficulties in the identifying the physical landmarks, and this would cause risk for the drivers and the people driving on the highways. So one of the key stakeholders were the drivers on the road because they would be relying on our prototype. The other would be U.S. Department of Transportation since they manages all the transportations. The third one would be law enforcement and first responders since low visibility causes there's higher chances of having more accidents. And lastly, the car manufacturer, because that's where they're going to implement our prototype design into the cars. So some of the user needs that we identified was user needs to stay in the proper lane in the harsh weather condition at all time of the day. The user should be notified of any deviation with an audio cue. This must follow all the automobile regulations. It must be implementable in varieties of car. And last but not least, it should be a low-cost solution.
Now moving on to our requirements that we define based off of our needs. There's one requirement that we actually didn't have testing for, which is the automobile regulations, but we still listed here because it would be important for moving forward if this were to be actually implemented in a variety of cars that would need to actually follow these standards. And the reason we didn't actually end up implementing that is just due to cost limitations as well as time, due to being a very lengthy process. And then all of these other requirements will go into more depth of how they're tested for our product in more detail later when we go over our test plans and how we're actually testing for them. Our overall proof of concept has changed a little bit from our first design review, and now it includes, instead of using an RFID system, it uses an RF module that communicates the data wirelessly to the car. So similar to the RFID system, it's still simulating like a tag number, except now it's using more of an active system due to this being a cheaper implementation for our project. And the solution itself uses the same sensor fusion that we've presented before, being the GPS IMU and the now RF module system. And here we have the final PCB product mounted inside of the car. And these would be communicating with the RF modules on the road, and it still plans to use the TSV reading to map to get the absolute position from the roadway. So this is our design path that we took for hardware. Starting from the beginning of the semester, we started with trying to design an antenna for the original RFID system. And then we had to implement that into our PCB as well as the speaker at the beginning of the semester. And then we spent the majority of our time reviewing the PCB schematic before doing the layout and then reviewing that as well. And then finally updating the components to make sure that they were actually in stock based on availability and doing a couple small revisions before we actually ordered it. And for assembling the PCB, we use the reflow process to be able to put on so we use surface mount components, which are very small, so it would be hard to solder by hand. So we use the reflow process to do that. And then after that, we did initial testing and implemented redesign to make certain things better and work properly. And we'll go into more depth on the redesign in future slides.
So throughout our implementation phase, there were varieties of design decisions that as like a hardware design team had to make. First of them was changes to the schematic and PCB, and that was to incorporate the newer RF module since we no longer are using the RFID because it's expensive and it's not within our scope of our budget for the project. Secondly, since we're not using the RFID reader, we had to remove all the text that we kind of wanted for our system to work. And for that purpose, we were just going to use the RF module, as John mentioned earlier in the slide, that would be just communicating between two modules wirelessly. Then we discontinued the usage of 12-volt power because that was mostly when we tested using directly 12 volts. We kind of our PCB broke, and because of that, we already had a backup plan that was using a micro USB cable that was used to flash the code onto the microcontroller. And lastly, there was no speech audio implementation for the speaker system due to the hardware limitation of our PCB.
All right, so on the software side of the project, our main approach throughout the semester was to pretty much tackle the functionality of the individual components first, before consolidating everything into one main algorithm, taking the logic that we had written in bits and pieces and putting those together. So at the start of the semester, we had our Raspberry Pi Pico, our GPS module, and our IMU module. We pretty much spent some time trying to use MicroPython to communicate with those and get data from them. And then once we got that down, we used those same techniques to work with our initial RFID module, which unfortunately didn't work. Didn't go as planned. However, we were able to use what we learned from that with our new RF module later down the line. However, in between the two RF approaches, Akhilesh and I did revisit the GPS and IMU after some time, and we worked on the Kalman filter, which involves just constant tweaking and some test drives around campus, making sure our arithmetic lined up and everything. And then later down the line, once we did get the new RF module working, we were able to create a CSV file containing data such as the IDs that they would transmit and their latitudes and their longitudes. And we could use those IDs returned from the modules to access that data from the file. So once we got that down, we were able to work with our speaker a little bit. So messing with the volume, the tone that plays, the rate at which they play, the pattern as we deviate. And then once we knocked all these out, we were able to consolidate the logic that we had written for all those into the main algorithm.
So this here is a breakdown of our overall program that will be run in our main MicroPython compiler. So first we would be starting the code, and from there, our first line would be to find the GPS coordinates. And this is basically an iterative process since we want the GPS to give us accurate coordinates of where the driver is. So until the GPS finds the coordinate, we would be searching for that. And once we do append the coordinates, we'll be able to know the driver's exact location in terms of latitude and longitude. And from there, we have specifically two cases where if we have an RFID and we don't have an RFID. Oh, and by the way, if we do append the driver's GPS coordinates, it is important that we know the heading of the driver so that because if the driver is traveling in the north-south direction, the latitude is going to be increasing and the longitude is going to be a specified width within the lane. And it's the opposite for when the car is traveling like east-west. And so as I mentioned, the two test cases where if the RFID is not found, we would be using the Kalman filter to obtain a prediction of where the driver is supposed to be at from the initial position. And from there, we have two specific thresholds that we have set based on the GPS and the Kalman filter. And if the right threshold is crossed, which means the car crossed the right boundary, we play the right speaker that is towards the right-hand side of the user. And if the car says the left threshold, it plays the left speaker. However, if we do find an RFID, we can easily obtain the balance of the RFID modules because it would be placed on either side of the lane. And it would contain an ID that we would essentially read in CSV files. More functionality on that will be on future slides. But essentially, if we cross the right boundary based on the data that is read from the right side of the RFID, then the right bound is crossed. So we play the right speaker, and the same for the left bound and left speaker display. So this is a detailed implementation of how our Kalman filter is supposed to be working. And so first we initialize the objects for the driver location and the Kalman filter. And then from there we obtain the GPS coordinates. And because our GPS is really important that initially that we use an initial coordinate, and from there we move on with the future coordinates. And our IMU would be constantly giving us acceleration data the more the car is traveling at. So at a certain period of time, we collect those data and we average it to get average it, and then we use a simple kinematic equation to calculate the position where the car is supposed to be at. And that delta we added to our initial coordinates Basically, the coordinates that were obtained initially, we add those deltas to know where the car is supposed to be at in a future spot. And at that spot, we also obtain the new GPS coordinates. So we compare the predicted location with the GPS coordinates. And from that, we could, after comparing it, we would basically know whether the car is in that location or not. And if not, we would know if they deviated, if they crossed a certain threshold, if they did. And this is basically, this process repeats again and again.
All right, so another part of the main algorithm that we want to dive more in depth with is our RFID functionality. And this mainly serves to determine what our bounds are on our right and left sides. And this is influenced by the direction. It's influenced by obviously what IDs we get, what rows we access. And so at the start of the main program, we initialize our RFID object, which contains all the UART and configurations and whatnot. And we also have our marker object, which will allow us to easily pull attributes of each row. So we can access the IDs, we can access the latitudes, longitudes separately, et cetera. And so when we initialize that RFID, we actually read through the CSV file and transfer the rows into an array of those marker objects. So it pretty much acts as a CSV file in a data structure form. And then we enter our search phase. So it's during this time where the transmitting modules that we have on the sides are just constantly transmitting their IDs. So for example, in our test, our one RF module had an ID of 1, so it was just sending out 1, 1, 1. The other one was sending out 2, 2, 2. And so what we do in this case is we pretty much just listen and we see if we can get 2 distinct IDs. We did set a timeout though. We set a timeout of about 2 seconds. And so if the RF modules aren't found, we just end the process and then we just rely on the Kalman filter instead. However, if we do find 2 distinct IDs, then we pretty much say, okay, go through the array and get me the markers with those IDs, but we don't need everything about the markers. We don't need the IDs, we just need the latitude, longitude. And then it's from here where we check for directions. Now, for simplicity in our test, we were mainly traveling north. And so we just had it hard-coded at north. However, if it weren't north, then we would just check for the other directions and that would change what we focus on. Would it be longitude, latitude, would our right bound value be greater than the left, or vice versa? However, in our case, it was indeed north, and so we would return that our right bound is the greater longitude value, and the left bound is the lower longitude value, and this cycle just repeats.
So now I will be briefly talking about the challenges during our hardware aspect of the project. So first challenge that we encountered was finding an approach after like the first RFID module failed. That was basically, it wasn't doing what it's supposed to be doing. So for this, we came up with like an RF communication, as we mentioned earlier, like a wireless communication that would consist of like a module and like a receiver on the PCB board and another transmitter that would be on the road. Basically, they would communicate wirelessly. And as Rifki mentioned, you need, for the software algorithm, you need the coordinates as your right bound and left bound. In order to incorporate the new module, we wanted to have some PCB traces. So as you can see in the picture here on right, like how there's like physical wire that we connected, because we already implemented like the PCB, we fabricated it with the older module's footprint. So now we wanted to place our newer receiver module on this. So we just added like a bunch of traces to connect the newer module. And another thing is during our testing phase, when we initially tested our first PCB, by directly supplying a 12-volt DC voltage, the PCB got broke. And after John and I debugged the PCB, we figured out that the high frequency noise from the rail might have caused the issue, since the filter that filters out the high frequency noise was not working as it's supposed to be working. And another issue that we also found out was one of the power component was not rated for the correct voltage. So that might have also caused the issue. And the issue was that the power plane and the ground plane were shorted together. So it was kind of hard process to figure out what we had to go individual components to check which component were shorted out. And finally, John figured out that it was the MCU that shorted out, and which was causing this shorting between the power and the ground plane. And that was some of the challenges that we faced as the hardware aspect of the project.
So throughout the semester, Keilish and I took on a handful of obstacles on the software side. So the foundation of our functionality for our sensors and the Pico was actually the communication protocols, namely UART and SPI. We had never worked with that before. Luckily, MicroPython had wonderful libraries and documentation for everything. But before actually knowing what to code, we had to understand the concept of transferring data and whatnot. And so it was a bit of a learning curve there, but after some conversations with John, we were able to grasp that concept and then get those coded. And then once we were able to get data, it was quite the challenge getting meaningful data from the IMU. So when reading the data sheet, the IMU gives back responses in 2's complement hexadecimal. There are sensitivity values based on the units that they return and the number of bits in the response. And so it was pretty much a question of, okay, how can we use MicroPython to take that raw response and then, have it converted to something that we can work with. And then once we did get something that we can work with, do these values make sense? If we're not moving the IMU, we don't want an acceleration of, 100 meters per second. And so later on, we got to work with our 2 RF approaches. And so in both of those cases, there was some documentation that was helpful to an extent. It gave us a set of commands that we could send out to configure and transmit and receive data. However, it was upon us to figure out how to do that using MicroPython and using their UART library. And so that took some time to learn, but eventually a new challenge with the new RF module was pretty much asking how can we get 2 modules to just constantly send data and then have the PCB module constantly just receive and listen. But we eventually got that down. And then lastly, the Kalman filter was just a whole nother beast. There was a lot of factors that came into play here. Early on in this process, we saw that our algorithm was a little bit off since our predictions were sending us about 5 degrees north and 20 degrees east. And Akilish and I thought to ourselves, okay, how can we fix this? What all plays into this? And so we eventually started to find that we had to make sure our units lined up since we had GPS coordinates in degrees and our deltas and our IMU data revolving around meters. And so we had to make sure that lined up. And then we also had to make sure our arithmetic lined up. We wanted to add and subtract at the right times based on our direction, because, if we're going straight constantly, our prediction shouldn't send us behind. And then lastly, we had to find that balance between spending time collecting samples for average accelerations and then getting the notification in time. So what we found was you could either spend a long time collecting samples, but then you're kind of late on the notification, or you can shorten your sample time, and get the notification out sooner, but there might be some false positives there.
So now we'll move into our testing plan. We'll start off with electrical. And here we have a table with the tests, the requirements of filling, and if it passed or failed. And one thing to note is we have 2, one that says it failed and another one that says test needed. For the one that failed, this was the one where it caused the redesign for the power to switch over from 12 volts to the 5-volt USB. The antenna design was because of the change in the RF module. We didn't need to actually design an antenna for the newer one we use later in the semester. So that the test is, if needed, if the design changes again, it could be still a useful test, but for our case, it wasn't. And then our other tests, like the RF monitor range and free space, was still useful so that we could test to see how far the new system could get. So we still use that one, even though it was a different RF system that it was operating slightly differently. And then the audio quality, we set it past just due to having a high enough volume so that it would be understandable, even though it didn't have the original vocals that we were looking for. For the mechanical, we also had a test that we got rid of, which was we had originally intended that we might need to move the RF module on the side of the car to read the tag, since it could be the car is a big metal box, so it could interfere with the antenna operating properly. But we found out with the system that we implemented, we didn't actually need that because we passed the original test before, which is reading the range with inside of the car. So if that one passes, we don't need to move on to making new housing to move it outside of the car. And then we also had a mounting the PCB passed, and that was just basically a test just to make sure that the PCB was sturdy and that it wasn't wiggling around more than it needed to within the car, so that it wouldn't mess up our sensor collection for the IMU and other sensors.
So this here is a compiled list of our major software test plans. So where the first 3 are just functionality tests, where we make sure that we're able to effectively read data from the IMU, and then it gives us, the GPS gives us an accurate location within a specified time. It doesn't take too long to give us driver's coordinates. And gyroscope, we did actually get the data from the eye view. It's just that we weren't able to incorporate it extensively into our main algorithm. But this could be implemented in the column filter for the future steps, and that will be discussed in future slides. So basically with these two working, our column filter can then be reliably worked on. So even that test, we were able to pass it after we got our effective data and testing it out. And from there, all these tests cover the RFID functionality. So basically for CSV reading, we're able to like cycle through a CSV file and we're getting data from it. And after we do that, we take it to the next level where we incorporate an RFID after checking to see if our RFID is properly transmitting the data, and we can actually see it within the code. And after we do see the RFID, we could then cycle through the CSV readings from the RFID reading that we obtained and find the specific coordinates that the RFID corresponds to. And that is this test right here. And after all this is we're able to accomplish, we could finally test the speaker, incorporate that, and see like going off the lane to see if the speaker gives out a warning in time and whether it's audible enough for the user to hear. And these are our integration test plans. So basically where we both combine the hardware and software together and we integrate a final system. So these two are like tests that would be done in the daytime, and these are in the nighttime. And then we had a last test that covered cold weather. So for the daytime test, we drove around in like parking lot and also in the roads during class times. And we tested out the Kalman filter and saw if like, lane deviations, it gave a specific distance that crossed the threshold. And we were able to see that our Kalman filter was giving a prediction estimate that was fairly close to what our GPS coordinate was also showing us. However, we did not try to, we weren't able to test out the lane lines covered in both daytime and nighttime because of the time constraint that we had on the project. And therefore, this is something that could potentially be done in the software team's next steps. And finally, we also tested for operational during cold weather. This was done towards the nighttime this is done towards evening time. And we even have a recording of it, which we will be showing in the later slides. So this here is an example of our test plan of our final system. Basically, we needed to pick a parking lot because we had to keep RFID modules on the road, and we felt it would be too risky to do it in an actual road. So we found a parking lot that would be empty parking lot that we would be able to test that. And we wanted to pick a parking lot so that we could travel in a straight line. So there is in the Google Maps, when you go in a straight line, it's not slanted. So you want to go as straight as possible, so the GPS gives straight data when we travel straight on it. And so that's why we chose the Jesse Owens Memorial Parking Stadium lot to test. And this is an example. This is how our test setup was basically at. So this is me and Rifty trying to like set up our system, and we basically drove from here after placing the RFID tags on either side of the lane. And this is how we tested. So basically we drove straight and then we deviated off left and right, and the speaker would be inside the car, and it would throw a warning if the car was supposed to cross off both the lanes. And the video on this is in a future slide in the demo. So these are essentially our results from our testing. So basically these bounds, this is the left deviation test where the car moved towards the left side of the lane. And these coordinates, so both of these coordinates were obtained from the RFID module. So these are the longitude. So this is the left this is the left side of the left lane coordinate, and this is the right lane coordinate. And this is where the driver is moving. And we would see as the driver moves closer to the left side, we would expect a warning at this particular point since it's really close to the left edge. And that is exactly what we expected. There was a warning that was shown right here. And the same for the next test as well. This is the similar test that we did for the right deviation. We saw that not only the left side, but the right side also showed similar results. And one drawback of this was our system wasn't really too consistent. Like we had to do multiple tries to actually read the RFID tags and the GPS to give us accurate data. So it took us multiple attempts to be able to get data like this. So I feel like one drawback of the system is that it's not too consistent for us to reliably move forward with this. So further testing and enhancements to the algorithm has to be performed before we can move on to the partners.
So a scenario that we also took into account for our test was the event where we wouldn't be able to find an RF module and we would have to rely on our Kalman filter. And so what we did to test this was we drove up north on High Street and we had our speaker, and what we did was we set our threshold to be 0.6 meters on either side, which is about 2 feet of room to move. And I'll explain these graphs in a bit here, but long story short, between these two coordinates, or between these two predictions, one worked out very well and the other one worked well at first. And so I'm going to start with that one. So over here we have our longitude prediction difference, and this is what our speaker revolves around, because when we're moving north and we change lanes, our longitude is changing. And so pretty much over here, whenever you see a positive value, that means that our prediction is sending us east. And when you see a negative value in the blue, then our prediction is sending us west. And so starting our drive, you may notice these spikes over here. That was from me slamming my brakes. And that is a detail that I'll get into when I talk about the latitude. However, once we straighten out, our prediction is pretty much the same as our current GPS coordinate. And so, it's predicting very well. A couple hiccups here, but, it's going well for the most part. And then I changed lanes to the right lane, which our prediction did get that right. We did move east. However, it was once I straightened out where it goes a little haywire. And it's around this time where my speed begins to vary. And also we could attribute some error to High Street being a little slanted. And so even though this worked at first, the error begins to accumulate and it just builds and builds. And so that didn't work 100% as well. However, our latitude seems to work out very well. So whenever we're traveling north, our latitudes increase. And so our predicted latitude should always be ahead, should always be greater than our current GPS. And we see that with all these positive values up here. However, with the negative values, we can attribute that to me hitting my brakes, because in our average acceleration samples, since I'm braking, that's a negative acceleration. And so our filter thinks that I'm way back there. However, as we can see, I brake, but then when I accelerate, it sends me up there. So at least there's some consistency in that case. And throughout my drive up High Street, we're generally predicting north and predicting ahead. And so long story short, even though that didn't go 100% to plan, we do see some potential in this Kalman filter, and it did actually think ahead in the latitude case as well. So in future steps, there could be some refinements made on the other end.
So with that, after the testing, we came up with a list of some of the shortcomings of the project that can be improved upon in further semesters, or if the project was continued. The first one is that the prototype has a longer latency than should be required, and that just attributes to it not like giving the response time as fast as it should be, so that the driver would have to react even faster than if the latency was shorter. Also, the prototype itself would need more enhancements for it to be functional for everyday users, because right now you need to specialized people to kind of operate it. So it's not really at a level where it could be commercially used. And along with that, the automobile industry standards need to be tested if it was going to be moved into more of a commercial setting. And then the assembly of the prototype in its current state isn't the easiest due to having to have modifications to the board. So even if it were like a good board shop that could place all the components, you still have to have someone manually place those wires and whatnot, which would be would be a big slowdown in the assembly. So more revisions of it would be needed to have a good assembly process streamlined.
So for the final part of the project, it was just since we were given a budget because we wanted to have our prototype to be a low cost. It came out to be roughly around $530. And the costs were separated with the prototype cost on the left table and the development cost on the right table. The prototype cost mainly includes the sensors that we had, GPS, IMU, RF modules, and bulk of the cost was also the PCB manufacturing cost and the miscellaneous costs that include the other ICs and caps, resistors, and some of the shipping costs as well. And for the development cost, we had just the breakout board that we needed to test our sub-level systems. And that was just GPS, IMU, and MCU development breakout boards that we had. It kind of looks like this. We kind of went above the budget, but this was mainly due to also shipping costs being higher during this time and some of the component shortage. So we had to order different components that were pretty expensive. So overall, there's still chances to be a really low cost implementable of this system. So now I would be just on the non-technical side, I would be talking about the project management. And to ensure that we all stayed on task and all the deadlines were met that were pre-established, we created a Gantt chart. And to ensure like all people were doing their task as they were supposed to do, we wanted to have like a layout of the overall project, which you can predict, which you can look at from the Gantt chart. And this highlighted rows here shows that those were the tasks that weren't achieved because there was changes to the schedule or there were changes to the requirement resources. And all these tasks were further like narrowed down to like a subtask. So people who have different expertise can work on simultaneously, as you can see here in parallel, that you can work on 2 tasks or 3 tasks. And this is just the second part of the Gantt chart. We also had the milestone table. So this is all the major deadlines that we had to meet for the course. And you can see we had the plan date here, and this is the actual date that we finished those all tasks. And one of the task milestone that we achieved was the testing full system milestone. And as you can see, the plan date was supposed to be the task should have been accomplished by October 23rd, but it delayed up until December 1. And this was mainly due to the RF module that we switched the design and schematics, and that pushed the overall task a little bit later into the project deadline. And this is just the Capstone 1 milestone table.
So now we have a list of the next steps for the hardware team, and this is based upon the shortcomings that we identified and how we would foresee those being improved. The first one would be if the budget is higher to redesign for the original system we intended to do, the ultra high frequency RFID system. And the reason for that is our current prototype will be more costly for infrastructure, but for making like a small project that was cheaper cost. But you'd want to move over to that system so that if it was going to be implemented, the infrastructure would be much cheaper. And then based upon if that switch is made or not, the PCB would need to be changed to either accommodate the current prototype, since the RF module doesn't really fit on it properly, or be switched over to the new a new RFID system. As well as changes to the PCB, some quick ones are adding the proper management to the 12-volt rail so that actually works and doesn't blow up the board. Moving the USB port to the edge of the board, because right now you have to like cut off the connector a little bit to get the plug in, so it wasn't on the edge. And we also thought that if we use a better MCU, because right now we're just using a really cheap MCU, that you could have better latency as well as better latency. And then if we had like a codec, we could do more audio processing with the better MCU to be able to do the bulk audio cues we were looking for. And also with the new MCU, we could add in or use like a different programming language that could allow us like use like a lower level like embedded C or something like that, so it'd be more optimized, so it'd run a little bit faster as well to improve the latency as well. And then depending on if the current RF systems maintain or not, like we would need to add a housing for them on the road, but ideally you'd still have to work on the housing if you were using tags and switch back to using tags on the road. So that's another step, just doing more mechanical housing to make the structural integrity of the overall system better.
So as I had mentioned several times previously, there are further steps that the software team could do to potentially enhance this project and basically expand the scope to different levels. The first thing would be to incorporate the gyroscope data within our algorithm, and basically this would be helpful in detecting lane deviations that occur at an angular rate. So, and that is currently a drawback of our system, since we do not account for like curved roads. And basically, if we are able to get the gyroscope data to do that reliably, it would be incorporated into the Kalman filter to account for the bends on the roads. Since the Kalman filter currently just uses the linear acceleration from the IMU, and we have to be traveling in a straight line because that's how the Kalman filter predicts the location in a linear fashion. So that's why the gyroscope, if that is the angular rate is also incorporated into the Kalman filter, then we can even account for bends on the roads and see if car deviations happen on the bends, then it's another test case that would also be satisfied. And then another thing is we could implement the logic to determine the driver's direction. And basically right now we have it set as that we manually know what the direction driver is traveling at. So from north to south or east to west, we manually put it in. But and we could probably implement logic to specifically know the direction the driver is traveling at, and this would potentially lead to like faster acceleration. Faster processing of our data. Next, since this was testing was done on a small scale level, we didn't really, and we also didn't have the resources. We were not unable to test with multiple RFID modules that were placed on the road in equal intervals. And basically, if we were able to test using multiple RFID modules, then this would probably enhance, we would know the consistency of our system in a better way, since right now we only test with 2 modules on either side of the plane. And next, in terms of the speaker, we could probably implement the .wav file for the speaker that basically consists of an audio file. And this is more of a user-friendly approach to like tell the user which direction to deviate off of. So if they're deviating left, then we ask the speaker tells them to go back to the right. And this is more like, it was helpful for the user to understand what the speaker is saying. And lastly, we could also test the RFID modules under various weather conditions such as ice, fog, and all that. And we were unable to test it this time because of our time constraints and due to the delay that we had in multiple aspects of our project.
So as we discussed last semester, as another step for just the project in general, we were thinking about potentially leaving our current RF approach and going back to the one that we initially planned. So just some background information and as a refresher, raised pavement markers, those reflectors that you see on the highways, on those lane lines are prevalent all throughout Ohio on the highways, and they're maintained on a fixed basis about 2 or 3 years. And seeing how prevalent these are and seeing how Ohio wants to expand their RF technology and their infrastructure, this is something that we can leverage for this project. So rather than having modules on the road that consistently transmit IDs like we do have in our current proof of concept, we could have instead RFID tags with these pavement markers and then an RFID reader in the car to transmit and receive and whatnot. Something I do want to stress though is that the RFID reader was a financial obstacle for us this semester. So that was another reason why we kind of went with the module-to-module communication, but ideally, this is something that would be great for the project in the future.
So some of the future consideration for our proof of concept is since it highly involves like a lot of sensors. So if the sensors fail to sense any like data, this would cause to like failure of the system, which would be a project management risk because it just fails the project. Other failure would include the RFID tags on road that not being read by the RF reader, and there would also be like a safety concern since we're going to be incorporating the RF reader in future within our system. Other safety risks are power supply overloading, which would heat up the circuits. There would be false alarm when notifying the driver, even though when the driver is not deviating. And lastly, it's the trade-off between the software efficiency and accuracy, because to achieve higher accuracy, you want to have like a iterating process for like the software, and that would take a lot of time, which would further delay the overall system reflex time.
All right, so to sum up our project throughout these past 2 semesters, modern day lane departure warning systems don't work in low visibility conditions, and this can put drivers on the highway in danger. And so it was our job to come up with a system, and we were able to design a system that combines GPS, IMU, and RF functionality, and use all this to track and estimate the driver's position, and also to gain somewhat of a sense of where potential lane boundaries might be. And that is all used to ultimately notify the driver of potential deviations without actually having to see those physical boundaries. And so regarding the project in general, there were plenty of things that went right and a few things that didn't go 100% to plan. And while we couldn't test this on, a large scale, like, a large corporation would in a way, we were able to construct this proof of concept here that you see on the right, and we learned a lot doing it, whether it was, electrical or software or even geographical concepts with latitude and longitudes that I didn't know about before this, or I didn't know I had to know going into this. But we also, as you saw, we also laid out future plans for this, and we're hoping that if another group takes us on, they just knock it out of the park. And so that wraps up our presentation. We do have a demo after this, But thank you for listening and thank you for your guidance throughout the semester. And so let's get into this demo.
You still need to watch it again, because I don't think there's anybody.
I want to-
Oh, okay. Oh, that's good. There's no one.
Because your laptop,
Um,
you can unmute that one and unmute yours.
Put it in full volume.